Hello, my people. Just wanted to do a quick video today, reviewing a little bit what we did Thursday and then kind of expounding a little further into some Pythagorean theorem stuff. We'll really hit it hard on Tuesday when I'm back in class. Hey, it's the final week I'm gone. Thank goodness. Been having a good time with baby girl, but excited to get some rhythm back with you guys, kind of switch it up and be here 5 days a week. Anyway, so learning target 5, what it was is the Pythagorean theorem, but using it for classifying. So of course you remember the Pythagorean theorem, a squared plus b squared equals c squared, right? So we know this was only good with right triangles, and kind of the key thing here was that it had to be equal, right? A plus b squared, the two legs of a right triangle had to equal c squared, right? They had to be equal. So if I square the a, square the b, it should equal c squared. Well, what if you tried it not on right triangles, but you tried it on any triangle? You took whatever the two shortest ones were, squared them, added them, and just see if they equaled c squared. What you would find is that if they were acute triangles, they would actually have the c squared part be smaller. So that would mean the a plus b part, a squared plus b squared part would be bigger if it was acute, or if it was obtuse, right? What if you did the a squared and the b squared, but the c squared was larger, so the mouth would go towards the c squared? So just a visual here with my red and blue, right? So what if you did a squared plus b squared? You didn't know that it was a right triangle, but then the c squared part ended up being, the c squared is smaller. The a and b were bigger than the c. So the c squared was smaller. Well, if you're using the same kind of lengths here, then you would get a smaller, so the 90 degrees, you would get an acute triangle. Or instead, if you did the a squared and the b squared and the c squared was bigger, if this opened up wider, if the c squared was longer than the a and the b, this would have to be a big obtuse angle. So the moral of the story is we can use a squared plus b squared equals c squared anytime on any triangle. We already know if they're equal, it's going to be a right triangle, right? 90 degrees, that's what the theorem is based on. But actually, if the c squared part is smaller, then it would be an acute triangle, and if the c squared was bigger, that would be obtuse. So we did that at the end of Thursday, but it was kind of rushed, so I just wanted to brush up on that. So any triangle, square the two smallest ones, add them together, and then just look. Is it equal? Is the c smaller, or is the c bigger? Okay. One thing we didn't talk about, and they're in your notes packet if you want to give 4 of them a try. I believe they're on the top of page 9. What about just like finding the missing length? So what if you knew they're right triangles, all right, but using a squared plus b squared equals c squared properly? We just haven't done that for a little while. So remember, the one across from the 90 degrees is the hypotenuse. So in this problem, that is c that we're actually looking for. We have a and b kind of interchangeable here. However, in this one, the c is 12. So that would mean a is 4. So in this problem, b is the question mark. So could we work backwards to solve that? So anyways, doing this one, we would have 5 squared plus 12 squared equals c squared. 5 times 5, 25. 12 times 12, 144 equals c squared. 25 plus 144 would be 169 equals c squared. And if you already don't know the answer, you could of course use your calculator to try and take the square root. But this is one you should know. Okay, Google, what's the square root of 169?
Square root 169 is 13.
Oh, thank you. So, wow, C would equal exactly 13. So, whenever you have 5, then 12, the hypotenuse would be 13. So, when it works out perfectly like that, when a right triangle works with solid integers, no decimals, no fractions, okay, that actually has a separate name called a Pythagorean triple. Okay, so there's a few of them and they're in your notes packet. Like the most famous one is the 3, 4, 5 triangle. If you have a right triangle, and this is 3 and this is 4, this is 5, because 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, which is 5 squared. So the ones that work are called Pythagorean triples. So you could write them like this, 3, 4, 5, or you could write it like 3, 4, 5. Okay, that's a triple. So this would be another example because it actually worked. So the 5, 12, 13 triangle would also work. What you're going to find out is that one like 6, 8, 10 also works. 6 squared, 36, 8 squared, 64, 36 plus 64 equals 100, 10 squared. However, this one really 6, 8, 10, 3, 4, 5, it actually just is the 3, 4, 5 triangle. It's just if you doubled every number, okay? So we wouldn't call it a 6, 8, 10 triple. We would just use 3, 4, 5 because it's just a ratio. It's just doubled the size. It's proportional. So there's a bunch of these and they're all listed on your notes packet and you can see them in the book. So basically the moral of the story is if it works out perfectly and you know it's a 90 degree, a squared plus b squared equals c squared, it works. We call those triples. These are the ones that worked and you usually write them like this. So like a 5, 12, 13 triangle. I think there's 7, 24, 25 triangle works and there's a couple more. I don't have them all memorized, but it's really helpful the more you know. 3, 4, 5 is probably the most important one. And then last but not least, let's just try this one. What's different is, again, we're working backwards on this one. Is it 5, 12, 13? Definitely not, because 12 is the c squared and this is 4. So I don't know if it's Pythagorean triple, but in this one I actually got to work backwards because we actually have 4 squared plus b squared we do not know equals c squared. Sorry, equals 12 squared because we do know c. So 16 plus b squared equals 144. So I'd have to subtract the 16 from both sides to get b squared by itself. So that would equal 128. We take the square root of both sides like we often do. I don't know about you, but that doesn't look good. Okay, Google, what is the square root of 128?
Square root 128 is approximately 11.314.
Oh, of course, 11.314, right? This is one of those infinite decimals that is an irrational number. So this is one where we would expect you to get the calculator answer and round, so approximately 11.34, I believe she said. But we'd also want you to be able to practice that simplifying the radical. So 128 is an even number. I'm guessing 2, 4, 6, 8, those go into it. I got to think, what is the biggest perfect square that goes into this? And I believe it would be 64. Yeah, 64 times 2, so that would have to be the biggest because it just cuts it in half. So this would be the biggest chunk, and then the square root of 64 would be 8. So it would be 8 root 2. So your answer would be 8 root 2 or approximately 11.34. So this side would be 8 root 2. All right, so it's a little bit easier to write that, isn't it, than the horrible decimal that keeps going on forever and ever. Okay, so there's going to be a lot of these in your homework tonight, and there's going to be a lot of these where you have to solve using the Pythagorean theorem. So make sure you're using your calculator if you need to, but when you use it and you get a terrible decimal like this one, make sure that you're also simplifying the radical as far as you can go. Awesome. I'll be back Tuesday. Then we got one solid week to make it till Thanksgiving break. And I hope you guys are gonna work hard all the way through. That way we can just relax, and then we'll take the Unit 4 test after Thanksgiving, okay? Thanks, peace. Can't turn it off on there. The watch went to sleep.